Okay, for this last part, we're going to go over a couple commands that are pretty powerful. But again, I want to emphasize that you do not want to rely on Mathematica alone to do certain computations. It turns out that if you want to know the convergence or divergence of a series, you can actually just have Mathematica sum it from 1 to infinity. And you can type in infinity, again, because it's a command, it's got to be capitalized. Shift-Enter, it tells you that it does not converge. Whereas if I punch in, for example, n cubed, it gives me something weird, but that actually tells me it converges. N squared also gives me something weird, but at least it converges, whereas 1 over n does not converge. So you can actually do it that way, but the reason why this is a little bit limiting is if I throw an x in there, then we're in a little bit of trouble. So we still need to rely on analytical techniques. And again, keep in mind that funny things happen towards infinity that we can't necessarily trust a computer with. Now, apart from series, there's a couple simple commands that might kind of entice you to look more into Mathematica. It'll do all the calculus you need it to do. So, for example, if you wanted to differentiate, the command is just d. So I can differentiate anything I want. So, for example, if I want to differentiate sine of x times, for example, e to the x. And notice I'm throwing in a lot of syntax here. And you have to put comma x to tell Mathematica that you're differentiating with respect to x. So it'll give you the derivative there using the product rule. You can also ask Mathematica to integrate, same thing, sine of x, e to the x, with respect to x. Before you had to use some crazy integration by parts. There's a bonus homework about it. But you can see Mathematica does it very quickly. But I do want to point out that it does have its limitations because let's say you were to integrate square root of x plus x cubed. Okay, it does give you an answer, but notice there's like an imaginary part here and something we call the inverse hyperbolic sine. So this really doesn't tell you anything. Even though you have this answer, you still are going to need to analyze it. So although Mathematica may give you the final answer, it might not all be that helpful, so we can't really rely on it in practice, but it does point us towards certain directions. And just one other extension. So with all the plot ones, so for example, we plotted x squared, for example, and simple parabola. And in a lot of these plotting, you can actually just put in plot 3D, and you can plot a three-dimensional shape. So now you can throw in an x, and maybe you can throw in a y. So maybe 1 over y squared. But what you're going to need now is you're going to need to specify what y goes from. I don't want to have it be undefined, so go from 0 to 3, or 1 to 3, for example, and it'll generate kind of a 3D plot which you can move around and kind of just check out what's going on there. You can also do parametric plots, and the syntax for this requires you to put in a function for x, so maybe t squared, and a function for y, so maybe t plus 3, and then you need to specify values of t. T goes from 0 to 4, for example, and then you can have it plot that. And similarly, you can do a parametric plot 3D, in which you just need to give it a third variable, let's say sine of t. And you can actually get a 3D shape, which isn't all that interesting, until you maybe throw in a manipulate. And instead of going from 0 to 4, you'll go from 0 to k. And you can let k go from 0 to, let's say, 6. So then what you can do here is you can get more of a view of how this trajectory evolves over time.